So now we're going to start on page 7. It's called Gas Mixtures and Partial Pressures. So this is Dalton's law. We did learn this last year. Okay, so how do we deal with gases made up of mixtures of two or more different substances? So this is where we get into, okay, just really common sense, to be honest, is Dalton's law. But then applying it, sometimes you just have to think and make sure you understand what's really going on. So Dalton's law just says that the total or the sum of the pressures in a container is the sum or the total of all the partial pressures. So the partial just means part, you hear the word. Each pressure, each gas has its own part of the pressure, and they're not the same necessarily, okay? So if you have a gas, or a flask here, and you have 3 different gases in here, it would have to be the total pressure in that flask would be pressure from the first gas, from the second gas, from the third gas, and you just add them up, and that's your total, okay? Now that's pretty easy. Now I know you guys got a question last year that was fairly easy like that, like just put them together, okay? Now we can read the rest of it there, but what I'm going to do is I'm just going to show you how this works, okay? So let's look at example 13 here. So first thing I do want you to realize is we're talking about vapor pressures in here. That means what? The pressure of the vapor. When do we use the term vapor? When the substance that we're looking at was a solid or liquid at room temperature but turned into a gas. So for instance, water would be an example of a vapor, which is what we're going to use a lot of. And water at room temperature would exist as a liquid. That's why we drink it. All right, so, and then it turns into a gas, obviously at higher temperatures, whatever. Okay, so that is why we call it water vapor instead of water gas. Okay, so one way to collect a gas sample is to bubble it through water. Now that's called gas displacement or water displacement if you use a gas, or really any item anyway. But we collect it through water. Okay, why? Because it's safer, because of ignition. Gases are a lot of times flammable. We can't see the gas, so we don't know what's collecting. If you remember last year, we collected butane. We took it and kind of inverted the graduated cylinder and collected it up the tube, and it bubbled. And we could see it because the water got displaced out of the tube. So here's the big thing is that you need to then, if you're talking about a dry gas only, when we're talking about, hey, let's collect nitrogen over water. So we want to know the pressure of nitrogen. We've got to subtract out the water vapor. So it's like, okay, if I collect nitrogen with water, then it's going to be, okay, the pressure of nitrogen is going to be in there plus the pressure of the water, since we use that to collect it. So if you want to know what's the nitrogen, if you know the total pressure, you just subtract off the water and you got the nitrogen. Okay, so that's what we're looking at. There are lots of signals in your problems about where you will have to do this subtraction. Collected over water, when we see that, is very, very clearly like that. You see it in 13 and then in example 15. A lot of times I'll underline it, but I don't have to. That just means, star is what I kind of do to myself, or underline it and just say, okay, for pressure that I collected at, I am going to have to adjust that by subtracting, okay, the water vapor. So the volume is read to be 596 centimeters cubed, or milliliters, at a temperature, okay, now we are going to use the Celsius to look up the water vapors, but usually in a problem we want to convert it, but we might wait here because we may not need it, okay? And we need a pressure, or we have a pressure right here of kilopascals. At a constant temperature, okay, here we go, guys. Okay, I probably shouldn't have underlined it. Maybe I'll go like that for a sec to say, okay, the temperature is not going to be included in this problem other than to look up the vapor pressure. So I'm just not even going to convert it to Kelvin. I would have, but I used it in the problem. What is the volume? So we're looking for a second volume. So this is volume 1, this is volume 2 that we're going to. Of this gas at, oh gosh, here's the big one, guys. You've got to know that that is giving me a number. It says that this is a pressure at standard atmospheric pressure. So pressure 2 is standard, where pressure 1 was 101.1 kilopascals. So what do we have to do here? We need the kilopascals. Standard in kilopascals is 101.325 kPa. That's the pressure. You guys know that. My lovely radio station, right? So you have to know that. Now, where do we make the adjustment? We make the adjustment where it was collected, because it's going to standard atmospheric pressure. That is not going to change. This original pressure, the pressure 1 that we collected it at, that we need to adjust first. So we're going to do our little star first here, collected over water. So we know that the pressure total, okay, is 101.1 kPas when they collected the gases over water. What does that include? That includes the pressure of, did not say what gas it was, okay, our gas, okay, plus the pressure of the water. All right, maybe I should just write dry gas here, okay, so we know, or we could fill it in if we knew what it was. So anyway, what are we going to do to calculate this? We are going to take, and I'm going to go up here so I don't run out of room, the 101.1 kPas, right? And we are going to, whoops, I just wrote it like really high there so it doesn't even look like a subtraction. We are going to take out the water because we want this left alone. So if it's being added, we're going to subtract the pressure of the water, okay? Now the pressure of the water, in this problem, I specifically did this. I know it's not fun, but usually I give you a number that's very, very quick. But if you go look, first of all, we're looking for kPas because our pressure's in kPa. Do we have a water vapor table at kPa? Well, we have two of them. We have one that's at millimeters of mercury and torr, so that's not kPa. And then what? We have kPa, so that's nice. But here's the thing. It's at 43 degrees Celsius. Now, it's not listed here, guys. All right? Now, there are a couple things. I mean, I could have went up here and looked, but guess what? Not listed either, so it's not going to help me, okay? But I know that it's between 40 and 50. So what I've got to do is I'm going to teach you a skill real quickly called interpolation. So it means in between the data, I need to find that data point, okay? There's also a skill called extrapolating, which means going beyond or extra from the data and figuring that out. So between 40 and 50. So here's what I need to do. It's 43. So we're going to go up here and do a quick little problem, okay? So at 40 degrees Celsius, we know that we're at least going to have this amount of pressure because it's over 40 degrees, right? 40 degrees Celsius, it is 7.4 kPas of pressure. So that would be nice and easy if that was my actual temperature, right? But it's not. So we have to know at 50 degrees Celsius, our next number that we know, it is 12.3. So it's going to be somewhere between 7.4 and 12.5. I'm always amazed that people put lower than this number. It's got to be at least this plus what, right? Okay, so here's what we're going to do. What do we figure out? Each degree is worth how many kPas if we're just averaging, okay? What we know here is that between 10 and or 40 and 50 degrees, it is 10 degrees difference, all right? So over that 10 degrees, what is the difference here? Well, the difference between these two is 12.3. Whoops, 12.3 minus 7.4. So that is a difference of 4.9, okay? kPa's difference. So what does that mean? You got to divide that by 10, right? And of course, you guys don't even have to do that in your calculator. 4.9 divided by 10, okay? So we take the difference, divide by the difference of degrees. That is going to tell me it's 0.49 kPas for every what? 1 degree. Whoops, I just wrote P twice, okay? For each 1 degree, okay, you go up. So we know that you add 0.49 kPas for every degree you go up. 43 is 3 degrees above 40, right? So we know we're going to start with, okay, the 7.4 kPas because that was at 40 degrees Celsius. Now I'm going to add what to it? Well, I need 3 degrees more, right? So plus 3 degrees more. Each 1 degree is 0.49. So I have to take 3 times 0.49. Or you could go and do the longer way and say add 0.49, add 0.49, add 0.49 3 times, right? But obviously multiplication is a shorter route. So I know that 3 times that 0.49 for every degree is going to give me a total of 1.47 kPas that I need to add to it. And 7.4 plus 1.47 is a total of 8.87 kPas. Okay, so I'm just going to plug in my water vapor. Does that make sense that it's 8.87? Of course, it's in between those. It's not halfway because it's only 43. Okay, so yeah, that makes sense. So now I just have to go back. Now, again, a lot of times it's much easier than this. You don't have to do this interpolation. Interpolate. That is a skill, though, I wanted to teach you. And that then we would just go ahead and subtract it off right away. They're a lot faster, of course. Okay, 101, your total, minus the 8.87 water vapor pressure. And the gas alone will be 92.23 kPAs of that pressure. So that is the dry gas. Okay, all right. So that's my adjusted pressure. All right. So now what that means is I don't put this in. So my pressure now is going to be 92.23 because what are we dealing with? Only the gas, that dry gas, okay? So here we go. Now we got to figure out what we got. We got volumes, pressure, volume, pressure. Now, remember what I told you, I always write vice president over treasurer when I see these kinds of problems. But do I have to write the treasurer part? No, I mean, it's just, I can write it for a second and say, oh, it was constant. I just needed it for the pressure, the water vapor, but I don't need it. So it's just volume times pressure equals volume times pressure. So 1 and then 2. So we just plug the numbers in, guys. So 596 centimeters cubed. Okay, you can put milliliters if that scares you less. The pressure one is that adjusted one. Now I'm just going to keep putting the star so I make sure you really realize, hey, we adjusted that. It's kPa. All right, now I got to make sure the units on the other side are the same. So what is the volume? Well, that's going to be, my answer is going to be in centimeters cubed or milliliters. That doesn't matter because I don't know it. And then kPa, oh, I set that up because I knew standard pressure, 101.325 kPa, is the same as the unit I have for pressure 1. So now it's just a math problem, right? So what do? We go to the side without the variable and solve first. So 596 times 92.23 equals. And then we're going to divide by, because it's multiply, we do the opposite to the side with a variable. Hopefully I hit that right. I probably should do it again, but I have a check over here. So it's 0.50 something something. Let's look at the sig figs and see if I need to go further. So we have 3 sig figs here for the milliliters or centimeters cubed, 4, and then more than that. So we're going to go to 3, okay? So that means the 5 does round that too. So 543 centimeters cubed, or like I said, you may put milliliters if that is your preference, okay? So that's just one example. It can be subtracting off as a big part of it, or it could be adding different gases or whatever to get what we need, all right? This next problem I'm going to do on a separate video or maybe in class. Just stay tuned.